All right, so we just learned this rule for differentiating inverse functions. All right, so another really common example of an inverse function would be trigonometric inverses. So, for example, let's say we have y equals sine inverse of x. Now, I'm not a big fan of this notation. In general, the inverse notation is super annoying because it looks like the reciprocal notation, but it's not. Notably, it is not 1 over sine. This is the inverse sine function, and I like to actually use the name arcsine personally, because I don't know, it's a little clearer. Also, it's not really a true inverse for the entire sine function, but just like a domain restricted version of the sine function. So I'm going to be calling it arcsine, and you'll see me using arc cosine and arc tangent and so on. Okay, so what we have in this situation is f inverse of x is the arc sine function, and the original function f of x would have been the sine function. And in order to apply this rule, we're going to need to know the derivative of the original f, which derivative of sine is cosine. So now we can take this information and put this together using this rule for inverses and say the derivative of the arc sine function is going to be 1 divided by the derivative of its inverse, the derivative of sine, which was cosine, of the arc sine function. And we got that. So that's the derivative of arc sine. However, that is not what you will see in the vast majority of textbooks. So actually, let's go a little bit further. Let's remember that arcsine is something which is a function which can be thought of as giving you an output, which is an angle. So let's let arcsine of x equal theta. Okay, then turn that around using the inverse idea and say x would be sine of theta. Okay, I know sine of theta usually is equal to the y coordinate of the point on the unit circle, so it's a little weird to be saying x equals, but it's just the particular name of the variable we're using in this case is x. So please don't be confused by that. I shouldn't even have mentioned it. So in this situation, x equals sine of theta, what we can do is set up a little triangle. This is a strategy that you may remember learning in trigonometry, where you set up a little right triangle. And you pick an angle and say, let's say that angle is our theta. Then we want to set it up so that sine of theta is x. And sine of theta is opposite over hypotenuse. So if I make this x and this 1, x over 1 would be the sine of theta, which is x. So I set this triangle up so that that equation is correct, right? Then what I can do is figure out what is the unknown over here. Let's call this one question mark. So question mark squared plus x squared should equal 1 squared by the Pythagorean theorem. And then question mark squared would be 1 minus x squared. And question mark should therefore be the square root of 1 minus x squared. Now this is positive, and I'm going to take the positive version here for this, but let me think about this here. There should be some situation in which this might be negative, I believe. Shoot. Not so sure. All right, well, I'm going to have to think about that and get back to you. But I'm going to write this out with a positive answer, and the plus or minus question I'll have to address in a future video or something. But okay, so that means this distance is the square root of 1 minus x squared. And now what we have right here, our derivative here, is actually 1 over cosine of theta, right? Since we said that arcsine of x was going to be theta. So the cosine of this theta from the triangle is adjacent over hypotenuse, which means this is 1 over the square root of 1 minus x squared. And that is the differentiation rule you will usually see. You will usually see derivative of arcsine, or sine inverse, is 1 over the square root of 1 minus x squared, like that. So it's kind of wacky, but this composition of a cosine with an arcsine does end up just being exactly the same as this algebraic function, the square root of 1 minus x squared. And that is kind of the explanation of where that comes from. So this is only one of the derivatives of the arc of the like inverse trig functions, but I was sending you out like a list of a bunch of derivatives, like a sort of a derivative cheat sheet that you can use sometimes for some instance, for working on homework, for example, and some tests when they're take-home tests. And you can also look at the list of these in the textbook as well, and you'll see all the different inverse trig derivatives.